In today's video, we're going to be looking at some tubing data with some flat bottom holes and some through wall holes. And the diameter of these holes is going to be increasing in a series of steps. And after a series of flat bottom holes with increasing depth, we'll have a hole, a through wall hole, just a single through wall hole. Then we'll put in a larger drill bit and a drill press. And we'll make some bigger flat bottom holes and then a bigger through wall hole. And we'll just keep doing that. And we're going to observe the phase and amplitude of the different signals as we step through them in the cal standard. So first thing I want to show you is the cal tube. Now hopefully you don't have any real tubes that look like this one, but this is a 9010 copper nickel tube. It's like, I mean, it's not 3/4, it's a 5/8, I don't know, 0.625 maybe diameter. But it's got some standard ASNT holes or flaws in this end. You got the 420s around the circumference right here. Then you've got a 60% flat bottom hole. Then you've got a tiny 0.052 inch in diameter single through wall hole. Then we've got a bunch of big holes here. Like there's 3 around the circumference here, and then there's also 3 around the circumference here. And over here I just got 1. Then here's one a little bit smaller. Then that's like the kindergartner pencil diameter. And that's like your collegiate automatic pencil eraser size. Then we got some flat bottom holes. Looks like there's 6 of them here with a smaller hole, but that's still a huge hole in terms of eddy current testing. And then as I would go down, I would just make the diameter of my drill bit smaller. Like that one's getting quite a bit smaller. And then we're back down to the 0.052 inch hole here at the other end with a 60 and the 420s. So I think to acquire this data, I'm gonna flip the standard over. So all the great big holes are going to be on the right end, or the last thing that we see on the strip chart. So I'm going to take my Core Star barnacle scraper bobbin probe, stick it in the tube. I'm going to hit start acquire. I'm going to null my test instrument right there. Push the probe through the standard. I exited the far end. So now I'm just going to clear the data. I'm going to pull my probe out nice and steady. All right. So we're just going to kind of step through this and look at the signals. And we're going to observe the phase and the amplitude changes. So the first thing we're going to see is the 420s. So what I'll do is I'm going to go up here and I'm going to hit null. Then I'm going to hit that button to bring everything on the screen. So this is all the data from this tube. Down here will be the 420s, 60, 100. And then we're going to start stepping up through all those different drill bit sizes. Obviously, the biggest holes are on the end. That's why you have the large signals kind of maxing out the strip chart here. Now, you may have read in your studies that signal phase and amplitude is related to the length, width, and volume of a discontinuity. So the larger your volume, or the larger amount of metal that's missing, like in the case of mechanical wear, the larger the amplitude of your signal is going to be. It's just going to be bigger. But what also has influence on the phase and amplitude, besides the volume, is the depth at which the eddy currents are disturbed. You probably remember from your studies that eddy current density is strongest at the surface. That's a skin effect. And as you decrease through the material on a given frequency, they're going to get weaker with depth, the eddy currents. The phase and amplitude of your signal is also related to the weighted average of all disturbed eddy currents at all depths. What that means is if you have an eddy current event right at the surface, you're going to have a signal with a phase angle that's closer to 0, or closer to probe motion, and it's going to be larger amplitude than if that same discontinuity was deeper in the material. Now, I'm not talking about a surface breaking flaw that grows deeper. I'm just saying if you had a small like inclusion or a small void, the further you move it down into your material, the more phase lag you'll have away from the probe motion, and the shallower or the less your signal amplitude will be. Now, the reason your signal is bigger and less phase closer to the surface is because the eddy currents at that level are more dense. They have more weighted input into the overall signal phase and amplitude. As you go deeper in the material and the eddy currents get weaker, they have less to say about the signal that's produced on your screen. So after all that word salad, we're going to go and just start stepping through these. So 20, 60, 100. So let me go to the bottom here. For this, I'm going to have to crank my window size down a little bit just to sort of isolate some of these flaws. Okay, display cursor. Now, I'm right on the 420s, but I can't see any flaws. It's because my span was adjusted a few minutes ago so I could bring these large flaws on the screen. So what I'm going to do is just go over here to 90 kilohertz, and I'm going to have to adjust that span so I can get the signals up to where we can see them a little bit, right? So, okay, there we go. There we go. Hold on there, Bessie. Same thing here. Let's make them a little bit larger. All right, so these are just 4 different frequencies. And we already said this one was the 420s right here. So if you measure that guy, 152, 105, 75, 57. It's rotating counterclockwise with decreasing frequency, which is what OD flaws do. So that matches our theory right there. We go up to the next flaw. It's that one right there. That's going to be the 60% single flat bottom hole. Same thing if we go measure it. There we go. 114, 80, 60, and 50. It's rotating counterclockwise with decreasing frequency. Textbook. Okay, then we go to the 100. Now here's where I'm going to have to crank my window size down a little bit because we're going to start to get into the busy part of this reference standard. So that 100, if I remember correctly, I should have set that fairly close to 100, or 40, I mean. 41, 41, 41, 39. Okay, so that's normally where you calibrate your single 100% through a whole signal. This one happens to be 0.052 inches in diameter. Again, here's where it starts to get busy. So I'm going to have a series of 4 flat bottom holes, each one a little bit deeper than the last, and then that same drill bit, but a through-wall hole. So let's see if we can see the 4 little ones. And it's probably easier even to see some of them on the strip chart here. See 1, 2, 3, 4, and then a big one. So the tiny one is kind of like right in the middle there. You can barely see it. Then we got a little deeper, a little bit deeper. Then we've got that 100%er. So the point I want to make with this one, let's make the window size a little smaller. So there's our 4 little guys. They're all rotating counterclockwise, decreasing frequency. And then you've got that big 100. And what I want to do here is measure the max rate on that guy. And look what happens to the phase. 33 degrees, 34, 37, 37. They all dropped a little bit. That's because the eddy currents are dense at the surface, and because the hole got bigger, more surface eddy currents are disturbed. So that's going to drop your phase. Next, let's see what I got to do here. Okay. We're going to go up to the next set of holes, which is going to be these ones right here. So you already know what the little ODs look like. So on the strip chart, we got the 4 or 5 smaller ones, and then we've got a bigger 100% hole. This is where I'm going to have to go and start bringing my span down so you can get them on the screen here. So obviously the bigger the hole, the larger the signal, because the signal amplitude is based on the length, width, and depth of the total volume of metal missing. So we know when the hole, which is through all, got larger because our drill bit has a larger diameter, the signal got bigger. And the reason the phase is dropping is because more surface eddy currents are disturbed than before. All right, so let's go there and hit max rate. 26, 29, 34, and 34. They dropped even a little bit more. So now we're getting up to the last two sets. Now, I don't know if you're writing these down or if you have a good memory, but if you can kind of remember what the phases were coming in at. Now we're at this set of flaws. 1, 2, 3, 4, 5, and then a bigger hole yet. So that's going to be that hole. Let's see if we can get a max rate in that. 21, 23, 30, and 33. See how they're still dropping? That's your weighted average at play. And then we've got, oh boy, that's going to be this set of flaws right here leading up to our massive damage part of the reference standard. So I got 1, 2, 3, 4, 5, 6. 6 little guys. 1, 2, 3, 4, 5, 6. A lot of these are, I guess, I don't know if they're, maybe some of them are too shallow that they're not showing up well. Oh, I see what happened. Because I had cranked my span so much in the less hot direction. Yeah, here's what it is. They're just not showing up on the strip chart because the span of the strip chart is very low. But here you can see 1, 2, 3, 4, 5 at least. 1, 2, 3, 4. So you got 5 of them there, right? So let's see what we got going on here. Measure. Okay, so if you look on your listed view now, we're going over the area where there's the 5 flat bottom hole ODs. And then we're going to get to this single hole right there. That's the one we're going to see what the phase is. I got to bring them back on screen a little bit again, just so you can see what we're talking about. All right, that's enough. There's 2. Let's just go to measure and hit max rate. 16, 19, 27, 30. They're dropping more towards surface or 0 degrees. And then finally, we're going to go to the next one over, which is even a bigger hole. So let's just go and measure this again to make sure we know what it is. 16, 19, 27, 30. Then we'll go to the next one. Okay, let's make the one this head a little smaller. I may have to do this twice because I have a really short-term memory, even though I'm an eddy current analyst. Let's see, cursor. So for the first one, we had 16, 19, 27, 30. 16, 19, 27, 30. 16, 27, 19, 30. 15, 16, 24, 28. See the larger diameter hole drop the phase even more. And then, it's still rotating up towards that smaller diameter 100% or the 0.052 hole, but the phase of each individual channel is dropping down more towards probe wobble. So 15, 16, 24, 28. Now the next one up here, I'm not right on it yet. Got to get on it a little bit better. 7. What's that? 19, 22, 26. See how they're dropping the bigger the holes get? And now we're kind of on our very last example. Because I couldn't get I think that's probably the largest drill bit I had in the case. That's probably why I stopped where I did. And hey, I'm also running out of tubing, right? I basically have 36 inches of tube full of holes. All right, so let's go back up here. It's like walking and patting my head and chewing gum all at the same time, talking and trying to manipulate all this eddy current data. we'll just bring the first couple on screen so you can see them a little bit better. Now I'm going to go in here, I'm going to hit measure, max rate, 7 degrees, 19, 22, 26. So hopefully by this demonstration, you can see that the larger the hole, more eddy currents close to the surface are disturbed, and that will drop your phase. So just because you got a signal that's, quite a bit less phase than what you set your 100 at, don't think that that can't be a big 100% hole, because it is. And one thing that gets people in trouble sometimes is when they got their spans so hot when they're analyzing data because they don't want to miss the small flaws. The big flaws will be so large in amplitude, they'll blow off screen and they don't even really look like a signal, like you'll never catch them. So that's why it's good to screen data on higher spans and lower spans, but not just one or the other, because you'll miss, you could miss large flaws with the low span, and you could miss small flaws with the large span. You get what I'm saying? I might have got that backwards. Anyway, I hope you enjoyed the video. Please like and subscribe to the channel if you find the content of value. And if you want any other videos, just let me know in the comments. I'll be happy to mock anything up for you. Thank you.